Physics Lab 2, Motion of a Fallen Object by Alexander Lavreniuk. Table of contents, as you can see, is here. So, introduction. This lab was aimed on learning how to predict and simulate the motion of the object that is fallen using GlowScript. Also, during this lab, we tracked the real-world motion of a fallen object and analyzed it. One of the main principles we used was Newton's second law. It states that the acceleration of the object depends on its mass and net force acting on it. As we can see, the object was accelerating during its fall, so we can understand that the net force was more than zero. And also we can understand vice versa, that if the object was on Earth, it was subdued to the Earth's gravity, and so its acceleration should be more than zero. And mass is also more than zero because it's a real-world object. So then let's go further and introduce you to the graphs of the results. I will go over what they mean a little bit later when we get back to them. So let's state the initial conditions. Initial velocity, initial position, and initial time are stated. The initial time is not zero because the video started earlier than the umbrella started falling. Then the system is umbrella, which serves as an object, air, and earth. So analysis of the object's motion, we use the tracker software, and I've tracked the movement of the fallen object, exporting the data about its position and velocity at each moment of time. Then the setup of computational model. I created three curves. Two of them, the first two were used as predictions. Prediction for including gravity and prediction for including gravity and drag both. Then the blue one is the experimental data. So then what we get, we import the experimental data, we split the array, we install the data time 1/30 seconds because that is the delta time in tracker between the frames. Then we plot first the curve of the real data, and after that we calculate the velocities and positions of both predictions and plot them. How do we do that? We calculate the drag force, and through that, knowing the mass of the object, we calculate the acceleration. So then we use it to predict the second velocity, which is the velocity including the force of gravity and the force of drag. And the first prediction is just velocity including the force of gravity. So after we plot them, we can see that predicted data without counting drag is green, with counting drag is red, and with experimental data, it's blue. And as we can see, let's go over the questions. Which models, if any, predict the terminal velocity? As we can see, the red one, or predicting with counting drag, predicts terminal velocity because terminal velocity is achieved due to the drag. And it predicts it quite nicely, starting from, I would say, 0.7 seconds in time. Then, what if the object was initially thrown downward? Would the terminal velocity in that case be similar or different from the case in the experiment? It would not be any different if the object was the same, because the only thing that the force of drag actually depends on is the Bose velocity. It depends on the mass, it depends on the drag. So the only thing that it really matters is the drag coefficient and the mass of the object, which, to be honest, is just dependent on the object. So if we use the same object over and over, it does not matter what speed is, what velocity is the initial, if still the terminal velocity will be still the same. So thank you all for the attention, and that's it.